Our next speaker is Dr. Jerry Shurson. Jerry is a professor in the Department of Animal Science at the University of Minnesota. He has developed a diverse swine nutrition and health research and education program that includes biosecurity and mitigation strategies to prevent transmission of swine viruses through feed supply chains. He also is leading efforts to improve environmental sustainability of pork and food production systems.
Well, thank you, Maria. It's a pleasure to be here this morning, and I want to just begin by saying that we've known for several decades now, I think, that certain pathogens can be transmitted through feed. Salmonella is a great example, I think, particularly in the poultry industry. But this whole business about transmitting viruses through feed is kind of a new frontier. We've really only been considering this for about the last 10 years. And so even though we've learned a lot, there are still a lot of questions, a lot of knowledge gaps, a lot of barriers that we need to overcome. And so what I want to try to review today briefly is some of the obstacles, challenges, barriers, knowledge gaps that I think raise a lot of questions about our current knowledge and how we move forward. I think one of the biggest things that we're dealing with is we're living with a lot of uncertainty. Still to this day, we do not know what the prevalence, concentration, or infectivity of viruses, if they're found in feed ingredients, are relative to manage it in global and domestic feed supply chains. We don't know. What we do know from experimental studies, either involving feeding inoculated feed to pigs or direct oral inoculation, is that for many of the viruses that we're concerned about, we have some minimum infectious dose estimates. Most of these range from somewhere around, let's see if I can make this work, 10 to the 4 to about 10 to the 7, with the exception of Seneca Valley, which may be a lower dose of about 10 to 2, 10 to 3. But what gets a little bit confusing is that we know that pigs eat multiple meals throughout the day, so they have multiple exposures, and even lower dosages of infected, potentially virus-infected pig can cause disease as more exposures take place. So one of the things I think all of us deal with is how do we translate or use experimental information and data and apply it to real farm or industry kinds of conditions, because the world's messy and getting predictable responses is difficult. I think the other really big challenge that I continue to remind people and we continue to struggle with is that we do not, in the feed industry, here in North America or around the world, have a system in place to accurately measure, monitor, prevent, and control, whether it's African swine fever virus, which our team has spent a lot of time working on with a surrogate, or other viruses like PED virus, Seneca, the list goes on and on. We don't know what that prevalence, concentration, and infectivity is in global feed supply chains. Yes, there have been a few studies, a few surveys, trying to document some evidence of real-world contamination in feed ingredients and complete feed. Study published a couple years ago focused on ASF transmission pathways in a large swine production system with company-owned feed mills in Vietnam from 2019 to 2021. The results were 0 out of 34 ingredients were positive PCR, and only 1 out of 102 finished feed samples were positive. The risk isn't 0, but this limited evidence shows that even in an ASF infected area, it makes us question what the prevalence of contamination is. I think we also need to spend time or back up sometimes. We as scientists get really focused in the micro sort of way, thinking about details of experiments and sort of things, but it's always good to take a step back and see the big picture and remember that the likelihood of pathogen contamination of a feed ingredient to cause disease starts with, first, the ingredient has to be contaminated with the pathogen. Then the pathogen has to survive the time and temperature conditions of drying, processing, and storage. Then it has to survive transport and subsequent processing and storage conditions at a feed mill in the manufacture of complete feed. And ultimately, depending on what the inclusion rate is of a contaminated ingredient, it has to be at a concentration in the complete feed that is greater than that minimum infective dose, or at least significant. And the pathogen must be in a viable form that's capable of causing infection. So there are a lot of steps that this contaminated feed has to go through from the time that it's initially contaminated until it ends up in the pig's stomach or digestive system to cause disease. Another area that I find a little bit challenging and troubling as I read through experimental studies, published studies, and our group has really tried to focus on this a lot, is that measures matter. What we measure and understanding what's behind a PCR, what is a viability PCR? Cesar was talking about that. Declan's been working on this a lot in our group. Understanding the mechanisms of what we're measuring is extremely important in how we interpret results and translate that into application. One of the examples that we can think about is that there are different kinds of assays and different kinds of tools that are used to measure viruses in various matrices. Feed ingredients are the topic of the day here. Some of them are in vitro measures like cell culture assays, which are artificial. Some are in vivo, which are bioassays involving lethality or infectivity. They're limited in sample size. And in situ measurements involving sampling infected animals, there are too many variables. So all of these measures are not perfect. They all have limitations, and we have to understand what those are when we interpret the results that we get from using them. Similarly, for the different tools that we use, the HAD50 and the TCID50 assays are commonly used to measure virus levels, concentrations in various materials, but they're indirect measures, they're not direct. We also use PCR, whether it's real-time PCR or others, along with ELISA and some other kinds of methods, and many of those lack context. So we need to back up and remember or learn what some of these different tools and what these different assays, how they're constructed, what their limitations are, and what those results from using them actually tell us. Ideally, I think we need to spend some time, and I'm not a virologist, this is not something that I would do, but many of you might have expertise and interest in doing these kinds of things. We need to find better testing methods, and our goal is to really accurately quantify the amount of viable virus particles capable of causing infection if ingested by pigs with high specificity and high sensitivity. And the high specificity means identifying negative results that are really negative, high sensitivity, identifying positive results that are truly positive. Again, trying to apply our laboratory findings to real-world situations, I think, depends on our understanding of these kinds of things. One of my other favorite phrases I often use with graduate students is don't just answer the questions, question the answers. And I think this whole new frontier of understanding virus transmission or potential virus transmission through feed really fits this scenario quite well. Let me give you an example. What does complete virus inactivation mean in the context of feed or feed ingredients? If you don't understand what inactivation reporting is all about, a lot of times as I interact with my friends in the feed industry, they'll say, well, gee, we got a 99.9% reduction by using this mitigant. That means it's almost 100%, it's all gone. I'm sorry, that's not what that means. It means that there's a 3 log or a 10 to the third reduction in virus, but it's not totally gone. And if the virus particles are still viable, they're capable of causing infection, especially if we start with an initial concentration of 10 to the 6. But again, remember, we don't know the prevalence, concentration, and infectivity of contamination in feed supply chain. So we don't know what a starting concentration might be in reality. But experimentally, we often start with 10 to the 6, 10 to the 7. And if we apply the minimum effective dose of ASF that Dr. Niederwerder determined a few years ago, experimentally, of 10 to the 4, that means that essentially we could be under what that infective dose might be, but we didn't account for my previous slide of pigs eat multiple meals throughout the day, multiple exposures. So is that 10 to the third remaining still capable of causing disease? We don't know, maybe. What else is interesting is that I really like this study that was conducted by some Spanish researchers a few years ago, where they fed diets containing liquid porcine plasma contaminated with African swine fever virus that provided 10 to the 4 to 10 to the 5th TCID50 virus particles per pig for 14 consecutive days, and it caused no infection. We need to be able to question the answers. We need to understand mechanisms of how these different assays work and mechanisms about how these viruses, the African swine fever virus in this case, might be transmitted or not transmitted based on some of the methodologies that we're using. We also have to remember that virus inactivation kinetics are not linear. They generally take a curvilinear shape, especially in feed ingredient matrices. The Weibull model, sometimes we'll get a shoulder response and sometimes we'll get a tailing response over the course of time by applying whether it's time and temperature or chemical mitigants. And that has implications for understanding what the residual remaining viable virus particles might be over some extended period of time or mitigation application. One of the other areas that's a really big challenge, and I understand kind of where this whole new frontier started, it really began back with the first PED outbreak in North America about 10 years ago, where spray-dried porcine plasma was implicated as a potential cause of that outbreak. And so that led to a whole cascade and series of experiments. And we know more about spray-dried porcine plasma and its safety. Now realize I said safety. It is very safe as a feed ingredient compared to most other feed ingredients we feed to pigs. And it's a really valuable ingredient. Soybean meal happens to be a more recent candidate for a lot of research, and we've learned a lot about it, but there's a whole bunch of other ingredients, folks, that we don't really understand how they fit into virus survival or inactivation relative to how we might approach it from a mitigation or biosecurity perspective. One of the things that we tried to do, and we were encouraged to do this, is Declan and Pedro and I put together a comprehensive review a couple of years, actually we published this I think last year, on biosecurity and mitigation strategies to control swine viruses and feed ingredients in complete feeds. And it was really a nice way to pull all this together and see that big picture, see where the gaps are, see where the barriers are. And part of where I'm going with this story is that up until 2022, 2 years ago, the US FDA did not recognize viruses as a potential reasonably foreseeable hazard in feed ingredients. Bacteria were, parasites were, fungi are, but they came out with a guidance for hazard analysis and risk-based preventive controls for food for animals, guidance for the industry. And even though that was a really remarkable milestone and a good step in the right direction, there's some problems. First of all, in Table 4-2, they rank viruses the least resistant to heat compared to bacteria, parasites, and fungal spores. Think about African swine fever virus, probably one of the most thermally resilient viruses we know, much more so than many of the bacteria that we deal with. So things aren't always as they seem. A little bit more problematic from an application point of view is that in order to put a preventive control plan in place, which is required by feed manufacturers under the FSMA guidelines, we have to be able to monitor and measure hazards or contaminants. What did I say earlier? We don't have a system in place. We don't have any commercial laboratories, no diagnostic laboratories that routinely measure viruses in feeds and feed ingredients. So implementing a preventive control plan is really difficult unless you can measure what you want to monitor. The other challenge is we don't know what the probability of infection or contamination might be in feed ingredients. And that's important because not only is probability important, but we probably have a better idea of the severity of what that would be. And those two things combined tell us what the importance or the legal requirements are relative to implementing this in a commercial feed mill. You can argue that, yeah, lots of different risk assessments have been done. PED virus and African swine fever virus are the two viruses that have been studied the most. I summarized here 6 different publications that have different kinds of risk assessments that have been conducted. The last 2 on the far right are recent ones from our group at the University of Minnesota. And the items that I've highlighted in red are those that are deficiencies, things that weren't accounted for that are really important to help us understand the risk of virus transmission through feed. Some of them weren't quantitative. Most of them, or many of them, don't have uncertainty estimates. And remember, uncertainty is a big part of the world that we're dealing with in this space. Some of them were not ingredient matrix specific, and some of those didn't even involve survival of infectious ASF and so on. For example, in the study that Rachel Shambaugh published as part of our group a couple years ago, we looked at soybean meal and corn importation into the US from countries that were positive for African swine fever virus. And because of lots of uncertainty, which we accounted for, and applying what we did know, the estimates for the likelihood of contamination is once every 21 to 1,563 years for soybean meal, and once every 66 to 5,000 years for importing organic corn from Romania, an ASF positive country, or soybean meal coming in from India or another ASF positive country. Those are pretty big numbers. The risk isn't 0, but maybe it's not quite as big as what we might think. We don't know. Lots of uncertainty. More recently, I really like this study because it was the first study ever to apply performance objective, which is used commonly in the food industry, that I think needs to be applied in a serious way in the feed industry to help us understand what the maximum microbiological concentration of a hazard in a food product at a specified step in the food chain is before it's consumed. This is a more advanced way of thinking about HACCP, okay? And In our study that focused on African swine fever virus and PED virus in spray-dried plasma, it showed that under the current production processing conditions to make plasma, over 95% compliance for standard production, and if you added an ultraviolet processing step, essentially there's no virus present based on what we currently know. It's a great way to help us really focus on individual ingredients and risk. We need more of that. The last example I'll give you, I really like this study as well because it talks about conditions in commercial swine farms, published by Galvis, and Cesar Corzo was part of this study. Porcine origin feed ingredients are not major risk factors for PRRS and PED outbreaks because the four major ones were farm-to-farm proximity, pig movement between farms, pig transport vehicles, and feed delivery vehicles. And so our biosecurity programs really need to focus on those, but also include, I'm going to argue, biosecurity of our feed mills and feed supply chains as well. So to me, one of the other big challenges is we know a lot. I mean, we've had some great presentations this morning about lots of details about biosecurity programs and protocols and putting these together to control disease transmission between farms and dead trucks and mortality and all those kinds of very, very important things. Unfortunately, I don't think we've really spent enough time in the feed industry applying those same principles to the feed supply chains that we're dealing with. We need, because we don't know and because of all this uncertainty, biosecurity by far, in my opinion, is the best approach to deal with the potential for virus transmission compared to relying on mitigation strategies, which can also be useful, but it's a shot in the dark because we don't know if the feed's contaminated or not. And it's an extra investment. So biosecurity programs are essential. The question is, do we have adequate biosecurity preventive controls in place? I would argue no. Part of it goes back again to our federal government not recognizing viruses as a potential reasonably foreseeable hazard. And so the Foreign Supplier Verification Program, which all feed importers must legally comply with in this country, does not include viruses as part of the requirements. Hopefully that'll change. The other part of the FSVP program that I've learned from working with feed industry groups is that there's not 100% compliance. And so we've got some opportunities here to do better. Now, a few progressive U.S. feed ingredient importers, to overcome some of these challenges, have implemented comprehensive biosecurity programs. Most of them have been focused on minimizing the likelihood of importing ingredients that may be contaminated with ASF. And they involve hazard analysis and risk-based preventive controls, measures, good agricultural practices. This is for organic corn produced in Romania on farms that may be exposed to wild boar populations. I've helped different groups put together reasonable biosecurity programs for that. Good handling practices, sanitary transport. We've learned that truck drivers are a big part of where the efforts need to be spent, whether it's talking about pig or feed. Good manufacturing practices, good warehousing practices, and certainly we need to have biosecurity audits. Just a few examples, and again, to emphasize that almost all the studies that have shown positive transmission through feed have involved truck drivers or trucks, not necessarily feed in itself. So sanitary transport by truck washing, disinfecting, drying, driver hygiene and documentation, one-way entrance and exits for loading and unloading, delivering to high-risk locations last, and then decontaminating. Feed warehouse and feed mill biosecurity, there's a whole long list of things that we can do there. Many of our feed mills don't have a very good biosecurity program, if any, and we need to work with those groups to try to implement some of these same kinds of things. Training people where to drive and walk, disposable footwear, many of the things that our previous speaker talked about, I think, are very, very relevant to the feed supply chain as well. We also have to teach the importance of hygiene and sanitation. And a couple speakers today have talked about using GlowGerm. It's a great tool to help with training and teaching people about sanitation and cleaning hands and feet and that sort of thing. So just a brief summary here before I finish up some other comments and leave it with all of you today. To me, biosecurity programs, prevention is the key. And once we get those put in place, and there's a lot of opportunity to do much, much better here than where we are today. Once those are in place and we're comfortable with that, then let's start talking about mitigation strategies. Because none of those mitigation strategies provide complete inactivation of viruses. They provide partial inactivation. Extended storage helps. Thermal and irradiation processing helps. Certain feed additives can be effective, others are not. And certain aspects of some of our feed ingredients, such as soybean meal and spray-dried plasma, again, can provide some beneficial effects to minimize adverse health effects under viral disease challenges in pigs. If a feed mill or facilities get contaminated with virus, they're really difficult to decontaminate. One of the unintended consequences that many people forget about or don't think about or ignore is that if we want to use extended storage as a mitigation strategy to reduce viruses in feed, temperature and time become important. Some of the things that happen with raising temperature, we start losing vitamin potency. We can reduce amino acid digestibility, lipid and protein oxidation can occur, bacterial growth can occur, mold growth and mycotoxin production as well, depending on moisture content. So we have to treat these feed ingredients not as these inert materials, but they have a purpose that we're trying to protect. And we want pigs to get maximum nutritional value out of whatever we're protecting. And so we have to take some of these other unintended consequences into account. We also know from a lot of the literature and previous studies that some of these key viruses are effectively inactivated, whatever inactivate might mean by your definition, at temperatures between about 60 to 70 some degrees Celsius for up to 30 minutes of heating time. And if we try to apply those kinds of temperatures to feed ingredients during storage, all the unintended consequences I talked about are really going to happen. And you're going to be really disappointed with the quality of nutrition that results from applying these kind of temperatures. I've highlighted African swine fever virus here because one of the other underlying themes of my message today is that things aren't always as they seem. We previously thought that 56 to 60 degrees C for 20 to 70 minutes was adequate for inactivating this virus, but we've learned that that's not the case, particularly with a lot of the work that our team's been working on the last few years at the University of Minnesota. Our foundational study that was published late last year, early this year, on the unexpected thermal stability of two envelope megaviruses, Amelia Huxley virus, which is the surrogate that we're using for African swine fever virus, and we're using viability PCR, give us a very different answer from what we've learned in the past. EHV, which I'll call it, is a really nice, safe surrogate for ASF because they have very similar structural characteristics. They're both double-stranded DNA viruses, very thermally resistant. And Declan can tell you a lot more about the history because he was instrumental in identifying EHV, what, Declan, 20-some years ago. The other thing that's even more, I think, fantastic about using it as a surrogate is there are three main points in this panel comparison I want to make. We compared using standard PCR, which is the far left-hand bar in both panels, versus viability PCR, shown in V. And notice that using viability versus standard PCR gives slightly lower values, but it's a lot more definitive because it tells us what the concentration of viable particles are. The second point of this story is notice that the pattern between these two viruses, EHV on the left, ASF on the right, are very similar, which makes them really good surrogates because they behave the same. Now, the most alarming, maybe, part of this comparison is that even at 100 degrees Celsius for 20 minutes, there was still almost 3 log of viable virus particles present. That's a whole lot more than what the original estimates of temperature and time indicated that were required for inactivating ASFV. We then confirmed using another technique called confocal microscopy that yes, in fact, intact virus particles are present in this mixture at 100 degrees C, and they're still viable after 20 minutes. So using this surrogate virus, we developed what we're calling the RISNA assay, and Declan may have talked about this during his presentation yesterday, which we can use to speed up the process of evaluating chemical mitigants and time and temperature mitigation strategies and other kinds of approaches, whether we're talking about complete feed and feed ingredients or decontaminating feed mills, but certainly we can use it to develop kinetics curves and estimate virus inactivation over time. And much of this work was funded by the United Soybean Board, the Fats and Proteins Research Foundation, and a number of other leading industry groups as well. We haven't published this work yet, but several companies are using this assay to evaluate chemical mitigants. Some of the mitigants, as you might expect, are effective, others are not. And so we need to sort out which ones work and which ones don't. And more recently, to confirm the use of this surrogate assay, this was a study funded by the United Soybean Board where we evaluated the effects of temperature from 4 degrees C up to 34 degrees C to simulate storage conditions over a period of time from 1 up to 120 days. And you can see the mean values and the box plots. There really wasn't much change, if any, in virus inactivation at the highest storage temperature for the longest period of time for this surrogate virus. So hopefully I've convinced you that the surrogate virus behaves much like African swine fever virus, and this tells us that we need to rethink the effectiveness of extended storage time under those kinds of conditions, not only for soybean meal, but in this study we included complete feed, corn fermented protein, DDGS, extruded soybean meal, high protein DDG, and soybean hulls as well, trying to expand our knowledge about different kinds of ingredients and how they behave. We also know, because we've studied, we, along with others, have studied PED a lot, and its potential inactivation during different kinds of feed processing methods. Pelleting, rendering of animal fats and protein byproducts, spray drying animal plasma, irradiation and extended storage are all partially effective in inactivating PED virus. Some of the other methods, extruding, expansion, desolventizing and toasting of soybean meal, steam flaking of grain, likely have some benefits because we're imposing time and temperature, but we need to validate those in experiments. So another major knowledge gap, Maria, in many things that we don't know yet. Some chemical mitigants are partially effective in inactivating ASF. Formaldehyde, medium chain fatty acids, and glycerol monolaurate are 3 that are consistently effective in these different matrices. We also know, and this is kind of an unexplored area that I think is really worth spending more time on. There are bioactive compounds in two of our key ingredients that we've studied a lot, soybean meal and spray-dried porcine plasma. In soybean meal, we have isoflavones and saponins. The University of Illinois has done some really nice studies, and Iowa State's done a little bit in this area as well, showing that feeding high amounts of soybean meal, and Paul, I'm thinking back to some of your comments earlier this year, feeding high amounts of soybean meal to PRRS-challenged pigs help alleviate some of the performance reductions that we often experience, and even mortality. We need to understand some of these functional or bioactive properties of natural ingredients. We also know that spray-dried plasma has a lot of bioactive compounds, and several studies have shown reductions in mortality, improved growth performance in PRRS-challenged pigs, reduced ASF infectivity, enhancement of immune response to ASF vaccines, which may be coming at some point in the future, and reductions in ASF transmission and disease progression. And certainly we know that, again, monoglycerides and some of our medium-chain fatty acid products also have some beneficial effects as well. Lastly, there are a lot of different commercial feed additive products. They're blends of either organic acids, essential oils, or medium-chain fatty acids in most cases, that most of these products have been shown to be effective at their recommended dietary inclusion rates to help ameliorate the health and growth performance reductions that we often see in pigs that are challenged either with PRRS virus, PED, or Seneca Valley. And we don't know about some of the other viruses, but there's certainly a lot of interest in the feed industry in developing these kinds of mitigation strategies. And really, I view them as useful tools, but they're kind of the last resort after we've tried to accomplish some of the other things I talked about earlier. So just to wrap up, prevention is the key. We must do better in developing and implementing biosecurity protocols for feed supply chains because we don't know which ingredients are contaminated, if they are. We don't know the concentration, and if it's there, we don't know infectivity. We need to question the answers more. We must understand the science associated with virus assays and tools and their limitations to avoid misinterpreting results and explore ways of improving these assays. Measures matter. We need to develop a system for measuring and monitoring virus contamination in feed for hazard analysis and risk-based preventive controls and FSVP compliance, and start using or considering performance objectives approaches for risk assessments of various processed feed ingredients. Things aren't always as they seem, and we're going to have to start thinking about how do we modify our existing biosecurity protocols around ASF and feed, because this virus is a lot more thermally resilient than we ever expected. And so there's a lot of knowledge gaps. We need to understand mechanisms which will help us figure out how to apply some of these and explain some of these different controversial or contradictory, I should say, results that we often see. With that, thank you very much.